Okay, hello guys, hope you're doing well. So as I mentioned earlier, while some people are joining us, I will make some announcement. So as I mentioned earlier, we had this meeting with professors who deliver uh, Physics 161 course yesterday, and so regarding midterm, so we will have it in time as I send you this message earlier today. So it will be Saturday. Um, Hopefully there will be no technical issues because there were some messages that server in C2 building will be shut down for some time. I hope it will work. Otherwise, if something happens, we will let you know. But so far, everything is going to happen according to schedule. We discussed this question regarding dropping the lowest grade for homework assignment and agreed on this statement. So your lowest grade from all homeworks assignments will be dropped, and it will not have an influence on your final grade for all homework assignments. Pretty much everything what is critically important. Do you have any questions, concerns regarding our organizational questions? Okay, good. Then I think we can continue, and let me change the
Excuse me, Professor.
yes.
Can I ask one question regarding the midterm exam?
Yes, sure.
So all of the exercises that will be tomorrow are based on the material on textbook?
You mean based on the material which
Covered.
which we covered during these weeks, and it's not exactly the same in terms of problems or some cases which we considered, but it will be in the topics of vectors, units, kinematics of like one-dimensional and two-dimensional motion. I'm not sure about dynamics, like Newton's laws of motion. Most likely they will not be included there, but in any way, we already covered this topic also. So it will be organized in a similar way as it was done with homework assignments. You will get similar problems and limited time for solving them.
Okay, thank you.
Here is a question: do we need to record ourselves during exam? No, you don't need to record yourself. There is, I mentioned about that before, that your IP address will be monitored, that it doesn't change. But other from that, I think that really not much other forms of control will be applied. So we believe that you will try to do your best not to cheat and solve problems by yourself. Which is eventually in your interests. You are here to learn things, not to learn advanced techniques of cheating. That's a good question. What means that IP address will be recorded. So I'm not sure about this technical part, how it's going to be realized and what exactly it means. I guess when you log in Logcappa, it has information on your IP address. So I think this was mentioned by our Logcappa administrator. So if you have specific technical questions about this aspect, you are welcome to contact him. How many problems will be in the exam? Yeah, that's not open information. So there will be certain number of problems which from one side should be reasonable. So you have possibility to solve them in this time frame. From my side, it should not be too little amount, a small amount of problems, because otherwise all of you can manage to solve them and get highest grades. So it will be some compromise. Will it be possible to return to previous questions during midterm? I guess it will be organized in the same way as homework assignment. So I don't think that there will be any technical difference, regardless the limited time. Okay, good. Seems that there will be quite a lot of problems. I mean, there will be as many problems as will be, and everyone will get the same amount of problems. So it will be for sure fair for everyone and randomly distributed in terms of, like, there will be some pool of problems and randomly distributed all over students with the same number of problems. No, you don't record yourselves, as I mentioned before. Okay, good. I think it's time to proceed further with our discussion. And let me change the camera. Yeah. So today we will start a new topic, which is work and kinetic energy. And let's see how much we can do today, but we will continue working on this and also potential energy and conversation of energy during the next week. So it's kind of another important part of classical mechanics, and very many problems can be solved by applying these concepts, which we're going to discuss during this and next week. Okay, so let us imagine some horizontal plane and three identical boxes on top of this plane. Let we apply to all of these boxes the same force by magnitude, but different in direction. So let's say, let it be something like this. Then we apply the same by amplitude, but different in direction here. And we have something like this. So when we are talking about work done by any force which is exerted on a body, we need to consider it not just only by its magnitude, which is of course important, but also in terms of its orientation with respect of its of the displacement of the body, which is caused by applying this force. So in other words, we need to consider how efficient this force is to move the body in the direction of its displacement. So it's obvious that, for instance, let's say it's 1, 2, 3, that force applied to body 2 is more efficient in moving this box to the right. Let's say this is our x-axis. Then force applied to body 1, because this force has two components. It has one vertical and horizontal component. So this horizontal component for sure will be smaller than the amplitude, the magnitude of the force itself. So, and in the case of the third body, this force is directed from top to down. And since we have this solid plane underneath, this body will not move downwards. So it doesn't matter how much we apply of this force, it will not move left or right. So we will not do any, this force will not do any work. So in general, we can write that work is proportional to the product between the force and displacement. Let's call it maybe, I don't know, yeah, delta x. So the main conclusion from here, doesn't matter which force by magnitude you apply to a body, if this force doesn't cause any displacement of the body, there is no any mechanical work done by this force. So means if you keep some heavy box steady and don't move with it, regardless that you will be quite tired after some time, you wouldn't do any work, because in that case you will just compensate the weight of the box, but your displacement will be equal to 0, so work is not done. And in more general form, you need to consider, in order to get like real value for work, you need to consider the projection of applied force to the direction of its displacement. What does it mean? That, let's say, let us consider one example. So here is a plane, here is some body. We apply some force to this body at angle alpha with respect to horizon. And while this force is applied, this body moved a certain distance. And we can put here vector values, so we can have some general equation then. So this is our force, and this is our delta R displacement. So the work done is the scalar or dot product of this applied force to displacement vector. And this is equal to magnitude of force multiply magnitude of displacement vector and multiply cosinus alpha of the angle between this force and displacement. So this is general equation for the work done by force. So we see that we have product of force and displacement, and that's why units for work will be Newton multiply meter, and Newton times meter is usually denoted as joule. So the unit which measures work is joule. And it's defined as Newton multiply meter. Okay, so what is also important here? The sign of work, so it can be, work can be positive or negative. So let us define how, when it's going to be positive and when negative. Imagine that you have a body, some force F applied from the left to the right, and this body has displacement delta R also from left to the right. In this case, when direction of force and displacement coincident, they are the same, mechanical work will be larger than 0, so it will be positive. Means that this force exerted to the body will do a positive work. If we have another case, when there is a body, we have force applied from left to right, but its displacement is from right to left, which can be, for instance, when we slow down the object, so it already moves, we apply some force to brake, like to stop it, but still it moves in the opposite direction for some time of the applied force. Then work will be negative, and means that applied force did negative work with respect to this body which moves in the opposite direction to that one at which applied force is directed. So this is the definition of positive and negative work. Now maybe let us consider here one simple but important example. So let's say we have some height, like some wall, and have a box. We need to do some work in order to move this box on top of this wall. So the height of the wall is h. So this box has some mass, so it has some weight, and obviously we need to apply some force to compensate this weight, and so it will be, if this is minus mg, so this will be mg. In order to move this box from the ground to on top of this wall. So what happens here? So we have axis x in this direction. So weight is negative. force is positive, our displacement will be positive because it moves from bottom to top. And work done by this applied force by us when we pick this box and put it on top of this wall will be the product of force and displacement. So since directions are the same, it will be all displacement and force directed along the axis X. We skip this cosinus alpha. We don't have any angle between force and displacement, and it will be mg multiplied h. So this is the work necessary which has to be done to move this box from ground to the top of the wall. So let us consider a different example. Again, also moving box on top of the wall, but now we have this wall and we have some inclined plane. This is our wall, inclined plane. So we need to move our body also from zero, from ground upwards. And we remember from previous discussions that in this case we have different components of this weight. So this will be reaction of the plane. Here will be mg cosine alpha. This is angle alpha. And here we will have another component, which is mg sinus alpha. So you see that if we now consider direction along this plane, there is some small force mg multiplied sine alpha, which is much smaller than weight of the full weight of the body. And in this case, it's easier to push the body than to pick it up directly, because then we need to apply force which is equal to the whole weight. And here, mg sinus alpha is much smaller than whole weight. There is a question. In previous example, we have some horizontal motion. Is it negligible? Yeah, sure. We don't consider horizontal motion here, so it was in one direction. So here we gain in force because we need to apply smaller force, but at the same time, this, like from here to here, we have the length of the plane, and this length of the plane has also a relationship to the height on which we finally need to put our body. And this relationship, like, is like h is equal to L multiply sinus alpha. So it's also right triangular. Here we have 90 degrees. So we can define h from knowing alpha by multiply alpha by sinus alpha. By multiply L, the length of the plane, by sinus alpha. And now let us consider what work will be done. So we know that work is the product of force to displacement. So this force is, so we apply here some force. which is equal to mg sine alpha to compensate this component of weight, and this body moves along the plane. So this will be mg multiplied sinus alpha. So in this case, it also coincides with the direction of displacement, this force. We don't have any angle between force and displacement. And displacement should be L, the length of all plane to go from ground to the top of this wall. And so we have a product here to L. And we can rearrange a bit here. So it will be mg multiply L sinus alpha. And from this equation, we see that this part is nothing else but the height of the wall. So it will be mg h, which is the height of the wall. And we actually got the same work needed to be done. Doesn't matter what happens, either we move the box from bottom on top directly, or we use this inclined plane. The one thing that with the plane, we gain in force, so we can apply smaller force, but then once we gain in force, we lose in distance. So we need to push this body during like a longer distance to make it on top of the wall. Oh, so there's a question, is force mg sine alpha like static? No, it's not static friction. We don't consider any friction on this plane. Mg sinus alpha is the component of weight mg of the body. So you see here is angle alpha. And if we consider two components of weight mg, it will be mg cosinus alpha, which goes perpendicular to the plane of the like surface of the plane and defines the reaction of the plane. And here is another component which goes in parallel to the plane and defines how much this kind of driving force which pulls this body down hills from the inclined plane. And we applied some force to compensate this driving force for sliding down, and that allowed us to move this body along the plane upwards. And the work done by this force will be mg multiply h, like h, and it will be equal to the case when we didn't use any plane. So the work is the same, but we can gain in either in force or in distance, and accordingly lose in the opposite moments. So let us go further and now consider so far we were considering only constant forces, but that is some particular case. It's not always the true. So let's consider some force which is a function of x, which is a function of applied of the displacement, or the position of the body. So in this case, let us show some graph. So this is coordinate, this is force here, and let it have some arbitrary dependence. So now it is not so clear how to calculate the work, because force itself is a function of x, so it changes, and we don't have constant force. However, in order to approach this problem, we need to consider some very small displacement like x plus small delta x, within which force doesn't change much and it's equal to its value at position x with very good approximation. So, and it is constant within this small displacement. Then we can write that delta omega, which is work done during this small displacement, is equal to constant value of f at coordinate x multiply delta x. So if this delta x is very small, the assumption that f as a function of x is constant within this range is true, because for very small change in independent variable, function doesn't change much, and it can be considered as constant value. So from this equation, it's clear that the work done during this small displacement delta x is the area of this segment. And if we want to consider some other location, we can also pick up here another small displacement. Here force will be also f as a function of x, but the value will be different because it changes. But also within this delta x, it will be constant. And the same way we can calculate the work done during this displacement. So when we want to figure out what work will be done when we move from x1 to x2 here, it's obviously that we need to divide this x2 minus x1, this interval, this displacement, in very small pieces and sum them up. So actually, like mathematically, it's called to integrate. So we, the work, like total work, which will be done by moving from point 1 to point 2, like x1 and x2, will be equal to integral of x from x1 to x2, our force as a function of x delta x. I didn't mention it before, but I believe it's clear, but in any way it would be better to mention that when I'm talking about any force F, I assume sum of all forces, and means that F is some resultant force which acts on the body. It can be one force, it can be like 100 forces, but we always consider the resultant force, which is sum of all forces. So here it actually should be vectors because these are vector values. Okay, so again, coming back to more general case, because here we consider only coordinate like one dimension x, but we know that force and displacement, they are vector quantities, and that's why in general case we can write that work is equal to integral from like point 1 to point 2, position 1, position 2, f as vector, and here we have like over delta r, which is displacement. So these vectors in the multi-dimension, which let's say we consider x and y, here we have unit vector I along axis x and unit vector j, along axis y. So then we can write that f vector is equal to fx as a function of x multiply I plus f y as a function of y j. So these are components of this vector. And also we have this displacement, which is equal delta xi plus delta yj. So taking into account that the integral of the sum is equal to the sum of integrals, we can finally write more applicable form of this definition of work, which is integral from position 1 to position 2, f x I dx I plus integral from position 1 to position 2 f y. So here indexes I forgot. F this f doesn't look good. Where did it? Oh, let's delete it. Okay, so it will be fy as a function of y, j delta y j. So in this case, yeah, we can split this integral in two and deal with the projections of components of force F to axis X and axis Y, and integrate it according to the displacement along this axis. Okay, pretty much everything we mentioned what is relevant to introduce the concept of work, and let's maybe do consider some cases specific. So maybe let's go to another slide. It will not be too crowded. And let's imagine we have a spring. Spring is a very good example. So we have a spring and some body attached to the spring. So here we don't consider any friction. It's like frictionless case. It is x equal 0. So it's...
Sorry, can you show the last slide, please, for a second?
Yes, sure.
Thank you, thank you.
You're welcome. So let's say under, like at t, some initial time, this spring is not neither stretched nor compressed. It's in equilibrium condition, and our mass is located at x0. So then let us assume that we applied some force and compressed the spring. So it moved to negative, so we have x-axis here. So it moved to some minus x with respect to 0. So then we let this spring go by itself, release the external force, and obviously when it's compressed, we know that spring force is equal to minus kx, where k is the spring coefficient, which defines how strong the spring is, and x is like the displacement of the spring. So this force is always directed to opposite direction of displacement, because we have this minus. So if we have displacement from 0 to minus x, it's from right to left, this spring will exert this force Fs from left to right. And let us see which work will this force do during the time this body will come back to its initial position at x0. So we let it go from this position 1 to position 2, which is initial position. So it will move from minus x to x equals 0, from minus x to 0. Okay, let us try to figure out to calculate the work. So work, we know that it's integral of the force as a function of x in this case, so it depends on the position. So we have this minus k multiply x delta x, and we have initial and final position. So initial will be minus x and final will be 0. So we interested what work will be done when this body reaches x equals 0. So let us integrate it, and it will be, so this is like k is a constant, so minus k could go out from the integral. We have x dx minus x from minus x to 0. So is this integral is minus kx squared divided by 2 from minus x to 0. So why I think that you should be aware of integrating very simple like function at least, and just to double check if this is true, we need to take derivative of this result of integration. So we should, by taking derivative of this function, we should over delta x, we should get the function which is in the integral. So we take derivative of k multiply x minus k x squared divided by 2, it will be minus kx, because these 2 will cancel each out, and instead of square function, we will get linear function when we take derivative of this result of integration. So this is the correct result of integration. And then in order to take this defined integral, we need to subtract from the final position initial position. So we substitute first 0 instead of x, so it will be k minus k0 squared, doesn't matter, divided by 2, so in any way it will be equal to 0. And then we subtract what was at the initial position. And we have minus, and this minus will give us plus k minus x here, but we have square, so this minus will be canceled by taking square. So it will be just x squared divided by 2. And this is equal kx squared divided by 2. So we see that this work, which is done by the spring force, is positive, and it's equal to k multiply x squared divided by 2. So why it's positive? So take a look here on this example. We see, like, obviously, if we compress the spring, it will move back when we release the force. So it means that now our spring force is directed from left to right, and our displacement will be also from left to right. So this work will be positive. Okay, so now we know that from, like, everyday life experience, that if we compress it, let it go, it comes back to initial case, and it continues to go, because here it has already some gained some velocity, so it continues to go to the further x, which is positive. In case of frictionless case, when we don't have any dissipation of energy because of friction, this displacement, positive displacement, will be equal to magnitude to negative displacement. So let us consider one more case. So our spring is stretched now, and this body moved from 0 already, where we considered work done by the spring from moving from minus x to x equals 0. And now we consider another section of this movement from 0 to plus x. Let us see what will happen. So during this interval, displacement still directed from left to right, because it continued to move from minus x to x. But since we changed the sign of x, so x now is positive. Starting from 0 to all values of positive x, this spring force will be now directed backwards from right to left. And you see that there is a difference in directions of displacement here and spring force. So it is expected that during this interval from 0 to plus x, work done by the force will be negative. Let's double check it with calculus. So here is work done by the force. Let's call this one minus x to 0, and this one 0 to x, equal to integral of minus kx, which is our spring force, dx. And now we need to consider different boundary conditions, like initial and final position. So initial position is 0. It starts, we consider work done from 0 to, by moving this object from 0 to plus x. And here it will be just x. Okay, we integrate again, so we get minus kx squared divided by 2. from now 0 to x, and this is equal to minus kx squared divided by 2 minus, so this is our final position, minus initial, this function at initial position, which is at 0, and will be k like 0 squared divided by 2, which is equal to 0, everything. And the result is minus kx squared divided by 2. So you see that this work done by spring force is negative. So work done by the same spring really changes its sign by depending at which position this body is located. So in the interval from minus x to x, when it was compressed and released, this work is positive. So here work is positive, and from interval from x equals 0 to x, work is negative. Okay, I believe you got the concept of force, and this example kind of solidified a bit your understanding. So recommend you to read definitely more, because our discussions are not self-contained in terms of material. So you definitely need more to read in the textbook. But this is, I believe, very important discussion on definition what force is and what work done by applied force is, and how things should be considered and calculated working in with work. Okay, I think this is enough for today. I wish you good weekend and a successful midterm. We will meet on Monday and continue our topic work and kinetic energy.
Mr. Victor, do we need to record ourselves when taking the exam?
No, you don't. You're not required to record yourself. You just get your task, do the solve problems within this interval of 1 hour. Submit the answers. Please keep in mind that all these rules for syntaxes, which is true for homework assignment, is also true for midterm. So don't use comma, and be very careful with dimensions, because long kappa will not accept your answers. So there's a question: can we check rules of long kappa from internet page? Yes, sure. Check in the manual file, which I shared with you long time ago and mentioned you many times about this file. There are links with a description of all rules from long kappa, and also there is a name and email address of long kappa administrator. So if you still experience any technical problems with long kappa, which I hope not, because it's already was enough time to be familiar with this software, contact him and figure it out. Okay, guys, have a good evening and good luck with your midterm. See you on Monday.
Thank you. Goodbye.
Bye.
Thank you.
Thank
Goodbye.
you. Bye.